Hello everyone, my name is Elton, and today we're diving into one of the cutting-edge technologies in the ZK space, Plonky3. Plonky3 is an innovative open-source toolkit developed by Polygon Labs Starkware Succinct that is pushing the boundaries of performance for ZK provers. Before we jump into today's workshop, let me first explain what Plonky3 is all about, why is it so powerful, and why is it a go-to tool for developers in the ZK space. Plonky3 offers incredible flexibility. It allows developers to create custom ZK VMs, zero-knowledge virtual machines, tailored to their specific application needs. Whether you're working on specialized financial instruments, gaming platforms, or supply chain management systems, Plonky3 enables you to optimize your virtual machines for maximum efficiency and functionality. So by reducing the time required to generate proofs, and it supports all those various finite fields and hash functions, Plonky3 basically enhances the scalability and the security of your applications. It makes it an essential tool for anyone looking to build ZK systems or ZK EVMs, like zero-knowledge Ethereum virtual machines. So now that you have a sense of roughly what Plonky3 is all about, why is it so valuable? Let's dive into today's workshop. Today, I'll be walking through a practical example where we'll be using Plonky3 to generate and prove a Fibonacci sequence. So this example was created by Brian Seong, so shout out to him, a DevRel at Polygon Labs, and he has done an amazing job showcasing the power of Plonky3 through this very straightforward yet insightful demonstration. So first and foremost, head to the repository and clone it. So you can do it simply by git cloning it and going into the repository and opening up with the code editor of your choice, right? In this very straightforward, as a simple Rust file is just denoted as main.rs. RS stands for Rust, and then you have obviously your cargo crates. He has very well documented the whole repository, but essentially it boils down to 6 steps. Bring it back up, right? 6 steps where you first define your program, you define your error constraints, the algebraic constraints, then the algebraic intermediate representation, and then afterwards you define your execution trace, and thereafter you choose your various field and hash functions. That's a beautiful part of the modularity, and then you write your ZK system setup, and last but not least, you just prove and verify. So in this first case, right, here you see we've importing a bunch of basically libraries, and here he has also, in a very nice sequential order, share the various steps. So the first step, which is to define the program, is basically, in this case, the Fibonacci sequence after like n steps. So the key requirements are basically a few. The program starts with both 0 and 1 as the initial input. Most of the CS students will know that. And in each iterations, you have 2 inputs and 1 output. The second input is basically the current iteration of the first input, and the second input is basically the sum of the current 2 inputs. So this recursively iterates n number of steps, and then the final results would be, of course, respective to the number of steps. So although this setup may seem very simple, actually it is a great way to actually understand the foundational concepts of ZK VMs, and this is exactly the kind of thing that Plonky3 excels at handling. So after you have your logic in play, you want to convert that into kind of the error constraints, right? Converting the program logic into the algebraic intermediate representation constraints, which then works with the execution trace, and this can be all visualized in the 2D matrix. So each row, right, represents an iteration of the computation, and the width of each of the row represents the number of elements in the entire computation. So in this case, width is 2 because you have 2, right? Fibonacci requires those two numbers to be added. The first few of the next row is the second few of the current row. So here you see the num steps and the final value are basically the number of steps of that you need in this Fibonacci sequence, and the final value that you kind of expect at the end of this like Fibonacci sequence. Here is the air script, the air constraints that actually defines the logic, right? So the starting values, of course, it starts with 0 and 1. Here you basically slice the matrix. The first row, of course, is denoted with 0, right? And then the next one is the 1, and it moves on and on. So it initializes with a starting value 0, 1, and then the state transition as it transit, right? What happens next is you can see here's the sum of the current values, and here's like the input of the other value. And then last but not least, you constrain the final value, and then you can assert it, right, to see whether or not it is as it is intended, the value wise. So after defining your business logic and your air constraints, right, the third step is to define your execution trace. Right, this involves tracking the state of the execution trace and each of the state of each iteration, and storing these states in a vector. And after you convert this, you have this 1D vector, you convert it into a 2D vector, a 2D matrix, so as to match the air script. Right, this execution trace is actually very essential, and it's actually the backbone of your ZK system, and it records the entire computational process. So this function here, trace generation, it just generate Fibonacci trace. All right, it of course starts with 0 and 1 as well. You know, it runs in a loop, it pushes the value, it does the stuff that Fibonacci is kind of expected, and it stores into, it converts into this 2D matrix, right, at the end. So that is the execution trace. And step 4 is choosing your hash and fill functions. So here, under main, of course, here is for logging purposes. You can see that you can customize however you like towards your specific application needs, as earlier mentioned. In this case, for simplicity, we are using the Mersenne31 as the fill function, using the Kerchak 256 as the hash function, right? We also have the Merkle tree for the polynomial commitments, and of course you have like challenger and free configurations here. So all this is a lot of cryptographic formulae that you can actually dive into deeper in the Plonky3 repository, right? But for the sake of simplicity for this workshop, I will not dive deep into the various cryptographic formulae, but rather how you can actually play around with this whole system. So actually selecting all this right fill and hash, it can actually enhance the performance and the security of your ZK VM. So let's not get bogged down into those details, and let's focus on writing the ZK stuff. So after you have defined your fill and hash functions, the next step 5, is to write your ZK system setup, right? Because how it actually looks like here at the last part, right, is where we do the Fibonacci, right, number of steps to find a value, and then to visualize this, I think it'd be good for me to kind of like write things down. So for the matrices, right, let me just, might be good to do this. Maybe. So how Fibonacci actually works is it has it goes row by row, right? So let's say row row 1, or rather row 0, row 1, row 2, row 3, row 4. And then you have, of course, when you have rows, you have the various columns, right? The columns is to show like the two input fields, right? So the first value is 0 and 1, as earlier mentioned. And then subsequently next, it becomes 1, which is, the second input becomes the first input. And the second input is actually the sum of the current two inputs, right? Which is still 1. So row 2 then becomes, it becomes 1, and this becomes 2, and here becomes 2, here becomes 3, and here becomes 3, here becomes 5, and so on and so forth. So in this example, Brian has already fixated for us two values, 8 and 21. So if you go all the way up, right, you have 5, you have 8, row 6, you have 8, you have 13, right, row 7, you have 13, and of course 21. And this is actually the final value that is expected to be the Fibonacci value at the end of the number of steps. Of course, here's 8 because start from row 0. So there's 8 steps. On the 8th step, it would be 21. So if everything goes well, when you run this whole Rust script, it should show an OK, so that it shows that everything's working fine. If not, it'll throw some errors, right? So let's actually use this whole setup that we have already defined and bring everything together and basically demonstrate how Plonky3 works for the Fibonacci sequence, right? So all you need to do is very simple. Bring up the terminal, and Brian has also already write a function that you just need to run, which is let me write, I think is where is it? Let me, easier to see from here. You just write cargo run, simple as that. So cargo run, it compiles everything inside the Rust file, the main.rs, and after compiling, right, it runs, and see that it has indeed run successfully, where it proved and verified pretty quickly. So if let's say you are inputting a different value, let's say if it's 20, right, it should throw an error. Save it, run it again, and indeed it did not assert correctly because it's wrong. Or maybe we could try a different value. Let's say the number of steps is 6, right? And the final value is 8, I think. Let's give it a go. And oh, my bad, 6, 1, 2, 3, 4, 5, 6, and 8. Not the power of number of steps. No, it needs to be a power of 2. But okay, nonetheless, let's revert back to, let's put like, maybe just put 2. Let's put 2. Let's put 0, 1. Put 2 here and 2 here, since power of 2. That is a debugging for another day. Nonetheless, let's go back to here, 8 and 21, verify it, run it, and it should be perfectly run. So as you have seen, understanding implementing Plonky3 requires attention to detail, right? To truly master Plonky3, you really need to deep dive into the technical aspects, and but once you do, you'll be well on your way to actually doing something very creative or innovative and pushing the boundaries of what's possible in the ZK or Web3 space. So if you want to follow along, check out Plonky3 GitHub repository, check out Brian's GitHub repository, and thank you guys for joining me. If you guys have any other questions, feel free to reach out to me, and happy coding!